This is Programming Chapter 2, Part 3. Now we're going to do some explanation of what the code is actually doing. So part of that is looking at scope as well, scope of variables. We're going to start off looking at some pseudocode. And that's just instructions in human form instead of doing it in a computer language. If you understand the pseudocode and you understand the syntax of the language, you should be able to convert pseudocode into an actual program. So when variables are declared inside a function, they're local to that function and only exist as long as it's running inside that function. As soon as that function exits, that variable is destroyed. If variables aren't declared inside any function, they're global and last as long as the program is executing. And we want to learn how variables are allocated. Now, inside the CPU, it executes one instruction at a time. So let's look at this. Before it executes this statement, A would be set to some random value or some unknown value. And as soon as it's finished, 24 will be put in A. Now the instruction pointer is at this spot. Again, B will be some unknown value. After this statement executes, B will be set to 64. We call the common denominator function. At this point, the code will jump to the common denominator function. So the instruction pointer will change. It's no longer in this routine. It goes to this routine. When this routine's done, it will jump back to the next line after the call. And it will print the common denominator of A and B. So how does it know how to get back? Well, there's a special type of memory called the stack. The memory isn't special in itself. It's just a special area we call the stack. It's the same as all the other memory. So how does that look? This is high memory. This is low memory. And generally your code sits down here. Your global data sits above it. Your stack is here. And it works down. This is static. There's nothing that happens with this. It's static. It doesn't change. And your heap is here. We'll talk about the heap later, but the heap goes up. Every time you allocate memory, the heap goes up. Every time you call a routine, it goes down. After you exit a routine, the stack goes back up. If you call lots and lots of routine, this will keep going down and down. If you allocate more memory, it keeps going up and up. If you free the memory, this will have more room for you. If you keep allocating memory and you keep calling functions without exiting them, you'll run out of memory because these two will crash and you'll get a memory error. So this stack is called a LIFO structure. That's because the last thing you put onto the stack, so you put something there. Anytime you get something from the stack, it gets it from the bottom. And every time you put something onto the stack, it puts it on the bottom. So let's look at this common denominator program. I've set a breakpoint at the beginning of the program. Let's run it. Okay, let's look at the stack pointer. And we have our watch variables. One thing that makes this easier to see is you can line up by 16s. And it's always best to start off at 0. It's easier to count from 0. So we see that B is at 40FE94. 40FE94, that's further down. 94 is here, and AA is FEA0, which is here. As I mentioned before, the compiler will put the variables wherever it wants, so you don't have to know the address, but it's not always where you might expect it. So let's step over that function. Like I said, it executes one at a time. 40FEA0, 40FEA0. It just has the value set. Before, all these were CC. This is in hexadecimal. We can change it to decimal. And you see the 24. Let's step over the next line. One thing you should actually see is the registers. Let's go into disassembly. This is the instruction pointer. Well, this is the memory addresses of the instructions. The instruction pointer currently is pointing at 13F5E55 here. So you can see the yellow. As soon as I execute one statement, the instruction pointer changes. And the memory changes. So 64 has just been placed in B. Okay, now we're going to execute machine language statements, because there's many machine language statements that make up one high-level statement, this C++ statement. So step, 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 step. Now it's going to call GCD. Okay, it's going to leave here and go to the GCD function. So we'll step into that. Hasn't quite got there. It goes through an intermediate step to get there. Now we're in the GCD function. We can see that the instruction pointer has changed. And if we look at the stack pointer, we're down at FDAC, so we're further up. And you can see that here we have another copy of B and a copy of A. So that got pushed onto the stack. We can see what else is on the stack by looking at hexadecimal mode. This is the return address. So we're going to return back to here. Let's look at the source. So it's going to check and see if B equals 0. It doesn't equal 0, so it means it'll come down to here. And we're going to do the GCD of B and A mod B. So we're going to step into this. And now we have the same values, but they're at different memory locations. Recall that we push these onto the stack. We'll just go up a little further. And again, we see 24 and 64. It's just swapping the values. This time B is equal to 24 and A is equal to 64. And we can see the return value where it's going to return to. So it's going to return to a different spot. This is 13F569C. If we go to disassembly, we can see that 13F569C is right after the GCD call. So that's how it keeps track. So we're just going to go into this one more time. You can see that the numbers are different now. B has a value of 16, A has a value of 24. And if we look at the stack, we see the 16 and 24 and the return address. So it's going to do this a bunch more times, but we're just going to skip out this time. Okay, so we've returned. And you can see that the values of A and B have changed. And if we look at the stack pointer, it's going back up. So we're at BF8, which is here. We go up again. The stack pointer is now FC00, so it's over here. And the stack pointer is going higher again. It's now back to CDC, so that's right there. And it'll just keep coming back, and now it's finally come back to the top level. So I know that's a little bit complicated, but if you understand how the instructor pointer changes, how memory's allocated, how you have different instances of these variables that are pushed onto the stack, you'll go a long way into understanding it. And of course, please ask questions if you're not fully sure. So you need to modify the sample program to loop and exit on a sentinel. Now it's easy to make everything global and not do any parameter passing, but when you have larger programs, that means you need more and more identifiers. It's also not possible to handle multitasking efficiently without local variables. So take the time to learn about scope. We're going to learn about creating objects and putting them into variables later. When you see an equal sign, this is not an equation like math. It's an assignment statement. If we did x equals x plus 2 in algebra, we can cancel out an x on both sides and we'd have 0 equals 2, and this is a false statement. In programming, if we have x equal to 7 and we say x is equal to x plus 2, this really means that x is equal to whatever the value is x is plus 2, and then store it back into x. So x gets assigned to 9 after this statement. And when you set variables, they'll take on different values as it's running. So that's why it's important to print these values to check if the values are changing as you expect. Or you can also use the debugger to examine variables as it's running. Visualizing code with flowcharts can make it easier to read, especially when you have a lot of branching. It's harder to follow code that's being indented. So we have indented code. Until you get used to reading code, you might have a tough time reading how the program flows. And sometimes indents are improperly done. So you can't always rely on the indents. Flowchart's pretty clear. Tells you that you just flow from one statement to the next statement. We'll be learning more complicated flowcharts as we go along. And that completes this lesson.